Have you ever just stopped and wondered how a machine, or, even your own brain, learns to make sense of the world? I mean, how can it pick out a single voice in a super crowded room or recognize a face from a blurry photo, all without a teacher walking it through the steps? Well, let's dive into this, because the answer is really beautiful, and it comes from this powerful idea in information theory that connects the logic of AI directly to the way our own minds might work.
So, to really get to the heart of this, we're going to focus on one big question. How does a machine learn to see? And I don't mean by just memorizing millions of labeled pictures of cats and dogs. I mean, how does it look at raw, messy visual data and start to figure out the fundamental patterns all by itself? Kind of like how a newborn's brain just starts processing the world for the very first time.
And that right there brings us to our first key concept: learning without a teacher. This is the whole world of what we call unsupervised learning. And honestly, this is where things get really, really cool. Unsupervised learning is pretty much what it sounds like. You give the system this massive flood of raw data, and its entire job is to find the hidden structure, the patterns, all by itself. There's no answer key, no labels saying this is a cat, this is a car, just the data. It's literally about finding order in the chaos.
Right, so think of the world as just a constant stream of mixed up signals, a chaotic blend of sounds, sights, you name it. The goal for an unsupervised system is to untangle this mess and pull out the original meaningful sources. But to even start doing that, the machine needs a way to measure what's meaningful and what's just noise. So how in the world do you measure something as abstract as meaning or structure? Well, it turns out information theory gives us this incredibly powerful language to do exactly that. And it all starts with a very simple, very intuitive idea.
The key is to measure surprise. That's it. Seriously, information isn't just about bits and bytes, it's about the reduction of uncertainty. So whenever something happens that you totally did not expect, you've learned something new. You've just gained information.
Let's make this super concrete. If I tell you the sun is going to rise tomorrow, that's a pretty low surprise event, right? It's super predictable, so you gain basically zero new information. But what if I told you it was going to rain frogs tomorrow? Whoa. Now that is a very, very low probability event, and if it happened, it would give you a massive amount of information, and of course a huge amount of surprise.
Now, the official mathematical way to measure this average surprise is something called entropy. A system with really high entropy is super unpredictable. Think of static on an old TV screen, total chaos. But a system with low entropy is predictable. It's structured. So the big takeaway here is that we now have a mathematical tool to actually measure the total uncertainty in any signal. Okay, that's great for one signal, but what about the relationship between two different things? What if knowing something about one tells you something about another? Like seeing dark clouds outside definitely tells you something about the chances of it raining soon. And this is where we get to the absolutely brilliant concept of mutual information. It's basically a measure of the shared information between two things. Just look at the Venn diagram here. It's that overlap in the middle. In our weather example, the mutual information between dark clouds and rain is really high. Knowing about the clouds seriously reduces your uncertainty about the rain. This one idea right here is the engine that's going to drive our whole self-learning system. All right, so let's keep building. We've got the tools to measure information, entropy, and mutual information. Now, let's see how a system can turn these measurements into an actual, powerful learning strategy. So, how does this all make the jump from abstract math to a machine that actually learns something useful? How does a system use these ideas to organize itself from scratch? Well, the logic is surprisingly simple. First, you just set a goal that's defined by information. For instance, a goal could be, hey, try to maximize the amount of information that flows through the system, or maybe try to minimize the shared information between your different outputs. And then the system just starts tweaking its own internal knobs and dials, trying to get better and better at hitting that goal. And it turns out one of the most powerful goals you can possibly set is to take some input signal and process it so that your outputs are as statistically independent as they can be. In other words, you want the system to minimize the mutual information between its outputs until there's basically no overlap left. This is the classic cocktail party problem. Just imagine you're at a party and you've got a bunch of microphones recording this big jumble of conversations. The goal is to take that messy, jumbled recording and somehow pull out each person's individual voice nice and clean. That is exactly what we're asking the machine to do. The technique for solving this is called independent component analysis, or ICA for short. It's this awesome method that takes a mixed-up signal and works backwards to find the original sources that must have created it. And it does this by making one big assumption,
that the original sources were independent. Then it just adjusts itself over and over until the outputs it's creating are as independent as possible. This diagram just lays out the mission perfectly. On the left, you've got the original independent sources, S. Those are the individual voices at the party. They get all mixed up by some process we don't know. The system only ever gets to see that mixed up signal in the middle, X. Its entire job is to learn how to build that demixer on the right, a network that can completely reverse the process and give us back the original clean signals. Okay, we have gone through the theory, from measuring surprise all the way to setting these information-based goals. Now for the payoff. Let's see what actually happens when we apply these principles to some real, messy data.
So does this stuff really work in the real world? Can you actually find a tiny hidden signal that's buried inside a massive amount of noise? Well, this case study with radar data is a perfect, and I mean perfect, example.
Okay, just take a look at the images on the left. This is raw data from two different radar polarizations. It is a complete mess of noise and clutter. That's all the shared, correlated information between the two channels. The target we're trying to find is totally invisible in there. Now, look at the right. This is what you get after you give the system one simple goal: minimize the mutual information between the two channels. By getting rid of everything they have in common, all that shared clutter, the unique, independent signal, our hidden target, just pops right out. It is an absolutely incredible result.
And this isn't just a neat trick for radar. These exact same ideas from information theory give us a really powerful explanation for how a system, whether it's biological or artificial, could learn the fundamental building blocks of vision just by looking at the world.
This idea was really explored in this landmark paper back in 1997 by Olshazen and Field. They basically proposed that the natural world we see isn't just random pixels. It's built out of a small set of basic components like edges and lines. So they created a system whose only goal was to find the most efficient way to represent images using as few of these primitives as possible. And when they let it run, something amazing happened. The system, completely on its own, taught itself to see the exact same kinds of edge and line detectors that we actually find in the visual cortex of the mammalian brain.
So let's just quickly recap this whole journey. We started by seeing that things like information and surprise can actually be measured with math. We then learned that by turning these measurements into goals, like, say, minimizing redundancy, a system can literally teach itself without any labels. And this process lets it pull out the hidden, meaningful structures from all kinds of complex data, which is not only a fundamental principle for building powerful AI, but it's also a stunningly elegant theory for how our own brains might learn to see the world. And that leaves us with one final fascinating question to think about. We've seen how these simple rules based on information can separate voices from a crowd and learn the building blocks of vision from nothing but raw pixels. So if these fundamental principles can construct something as incredibly complex as perception, what else are they capable of building?